You have two sorted lists of numbers, and the task is to find their combined median, the middle value if you merge them together in order. The catch is you need to do it fast, in logarithmic time rather than just merging and scanning the whole thing. Beginner level, high. If you've never seen this kind of problem before, don't worry, we'll go slow. Most people's first idea is to combine both lists into one big list and look at the middle. That works, but it's slower than it needs to be. There's a neat trick that finds the answer without ever combining the lists. By the end of this video, you'll understand exactly how it works, step by step. This problem shows up a lot in coding interviews at big tech companies. It's labeled hard or LeetCode, but don't let that scare you. We'll break it into small, easy pieces. It's also similar to real-world situations, like when a computer needs to combine two already sorted lists of data quickly. And the main technique we'll use, called binary search, which just means repeatedly cutting your search area in half, is something you'll see again and again in other problems. Let's define our terms first. An array is just a list of numbers. Sorted means the numbers are already arranged from smallest to largest. We are given two sorted arrays called nums1 and nums2, and we need to find the median. That's just a fancy word for the middle value inputs of all the numbers combined. Here's a tiny example. If nums1 is 1, 3 and nums2 is 1, 3 and nums2 is 2, and you combine them, you'd get 1, 2, 3 and. The middle number there is 2, so the middle do 3. The median is 2. Easy, right? The large part is that we are not allowed to actually combine or merge the lists. That would be too slow for large inputs. Let's slow down and nail down 3 words before we go further, since we'll use them a lot. A sorted array is just a list of numbers already arranged from smallest to biggest. The median is the middle number, once everything is lined up in order. If there's an even amount of numbers, it's the average of the two middle ones. And binary search is a way of finding something quickly. Instead of checking every single option one by one, you make a guess, see if you should look higher or lower, and cut the number of options you're considering in half each time. Keep these 3 words in mind. We'll lean on them the whole video. The most natural idea is take nums1 and nums2, combine them into one sorted list, and then just look at whatever number sits in the middle. This absolutely works, and it's simple to write. But let's see what happens when the lists get really big. That's where the trouble starts. Combining the two lists means we have to look at every single number in both lists at least once. In computer science terms, that's called linear time, written as OM plus n, where m and n are the sizes of the two lists. But this problem specifically asks for something much faster, called logarithmic time, or O logarithmic time. That means the time barely grows even if the lists get huge. So we need a completely different approach, one that doesn't have to look at every number. Here's the big idea, and it's simpler than it sounds. Instead of merging the lists, imagine making one cut in each list at the same time, like slicing both lists with a pair of scissors so that everything to the left of both cuts combined is exactly half of all the numbers. If we can find a cutting spot where every number on the left side is smaller than or equal to every number on the right side, we found our answer, with no merging required. To find that perfect cutting spot quickly, we use binary search, remember. That means guessing a spot, checking if it's right, and narrowing down from there, but only on the smaller of the two lists. First, a small housekeeping step. We make sure nums1 is always the shorter or equal list, swapping them if needed. This keeps the amount of guessing we have to do as small as possible. We are going to binary search for one number. How many elements from nums1 should go on the left side of our cut? This is called the partition. Once we know that number for nums1, the partition for nums2 isn't really a choice anymore. It's whatever number makes the left side add up to exactly half of everything. Here's a way to picture this. Imagine each array is a row of playing cards, and you're sliding a little divider through each row. You don't need to look at the whole row. You only ever need to peek at the card just to the left of the divider, and the card just to the right of it, in each row. That's 4 numbers total, and we give them names, left 1, right 1, left 2, right 2. We guess a spot I is in nums1 for our divider. We guess a spot I is in nums2, gets calculated automatically so both sides stay balanced. If a divider happens to sit at the very start or end of a list, there's no card there, so we just pretend it's negative infinity or positive infinity. Now we check, is left 1 smaller than or equal to right 2, and is left 2 smaller than or equal to right 1? If yes, we found the perfect cut and the median is sitting right at that boundary, we just do a little math to grab it. If left 1 turns out too big, that means we included too many elements from nums1 on the left, so we nudge our guess smaller. Otherwise, we nudge it bigger. This is exactly the same narrow it down idea from binary search, just applied here. And that's it, the same narrow it down idea from binary search, just applied here. And it's it the Nusturn turns out to like. Let's practice with a tiny example by hand before I show the answer. This really helps it stick. We have nums1 equals 1, 3 and nums2 equals 2. Pause the video if you can, grab a pen and try walking through the steps yourself. Where does the divider land in nums1? What number j's does that give you for nums2? And what median do you end up with? Take a guess, then let's check it together. Let's trace it together. When I equals 1 and j equals 1, we get left 1 equals 1, left 2 equals 2, right 1 equals infinity. Nothing is left in nums1 and right 2 equals 2. Checking our rule, is left 1 1 less than or equal to right 2 2 2 2? Yes. Is left 2 2 2 less than or equal to right 1 infinity? Yes. So this is our answer. Since there are 3 total numbers, an odd amount, we just take the bigger of the 2 left values, which is 2. That matches exactly what we got earlier by simply merging the lists by hand. Great, our trick works. If you're using this for interview practice, here's a simple tip. Start by saying the easy merging idea out loud in one sentence. Then, right away, mention how slow it is. OM plus nen before the interviewer even has to ask. Then say something like, but we can actually do better using a partition trick. Bringing that up yourself without being asked shows the interviewer you really understand the problem instead of just having memorized an answer. Let's compare our two methods side by side. The merging approach takes time proportional to the total number of elements in both lists, and it also needs extra memory to store that new combined list. The partition trick we learned only takes time proportional to the log of the smaller list size, much faster for big inputs, and it doesn't need any extra list at all. So going forward, reach for the partition trick whenever speed matters, and only use merging as a quick way to double check your answer on a small example. Let's double check our solution handles some tricky situations. What if nums1 is completely empty? No problem, our infinity placeholders take care of it since the divider I just stays at 0 the whole time. What if one list is way bigger than the other? Also fine since we always binary search the shorter list, so it never slows down. What about repeated numbers appearing in both lists? Also fine, remember our check used less than or equal to, not just 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 less than, so ties this in some place. Let's quickly go back over everything. We started with a simple idea of merging both lists together. It worked, but it was too slow once the problem asked for log time. So instead, we learned the partition trick, use binary search to find one perfect cutting spot in the shorter list, check just 4 numbers around that cut, and once the left side's biggest number is smaller than or equal to the right side's smallest number, we're done. And it's fast. Nicely done for following along through all of that. New videos drop tomorrow. Same time, I write these alone at a desk. A like tells me it landed. A like these alone at a desk. A like tells me it landed. A follow means come back tomorrow. Intermediate level. Everyone's first instinct is to merge both arrays and grab the middle. But there's a way to find the median without ever combining them. By the end of this video, you'll spot this cut point trick in seconds. This is one of the most famous hard problems on LeetCode, and interviewers love it because the brute force feels done way too early. It also mirrors real systems that merge sorted logs or sorted database shards. If you get comfortable here, binary search on the answer becomes a tool you'll reuse everywhere. We get two already sorted arrays, nums1 and nums2, and we need the median of everything combined. For nums1 equals 1, 3 and nums2 equals 2, if you merge them you'd get 1, 2, 3 and the median is just the middle value, 2. The catch is the merge itself is too slow, we're not allowed to do it. A sorted array just means the numbers are already lined up smallest to largest, like a sorted array. The median is the middle number when everything is lined up. Binary search means instead of checking every option, we keep cutting our search space in half. The obvious idea is to merge nums1 and nums2 into one big sorted array, then just index into the middle. This totally works, and it's easy to write. But watch what happens to the time it takes as the arrays get huge. Merging takes time proportional to the total size of both arrays. That's big O of m plus n. The problem explicitly demands big O of log of m plus n. So we need something that doesn't touch every element. Here's the trick. Instead of merging, imagine slicing both arrays at once so the combined left half has exactly half the total elements. If we find a slice where every left element is less than or equal to every right element, we're done. No merging needed. We binary search on where that slice goes in the smaller array. We swap so nums1 is always the shorter array that keeps our search space small. We binary search over how many elements of nums1 go into the left half, called the partition. Once we pick that number, the partition of nums2 is forced because the left half always needs exactly half the total elements. Picture both arrays as two decks of cards laid out in a row, and you slide a divider through each deck. You only ever need to peek at the card right before the divider and the card right after. In both decks, that's 4 numbers total. We guess a split point I in nums1, and j is whatever makes the left half exactly half-sized, using infinity as a stand-in, when the divider sits at the very edge with nothing there. If left 1 is less than or equal to right 2 and left 2 is less than or equal to right 1, this cut is correct and the median sits right at that boundary. If left 1 is too big, we shift our guess left, otherwise we shift right, just like normal binary search. There's the pattern, and that just dropped us to big O of log of m plus n. Clean. Quick pause before I show you. For nums1 equals 1, 3 and nums2 equals 2, walk through the loop yourself. What partition index does it land on and what median comes out? Hold that thought. We'll check it right now. With I equals 1 and j equals 1, left 1 is 1, left 2 is 2, right 1 is infinity, right 2 is 2, and the condition holds. Since the total length 3 is odd, we return the bigger of the two left values, which is 2. Matches our merged array answer exactly. Here's the move that actually lands in an interview. Say the merge idea out loud in one sentence. Immediately name its O of m plus n cost before the interviewer has to ask. Then pivot yourself into, but we can do better with a partition. That pivot, offered without being prompted, is what signals you're not just reciting a memorized solution. The merge approach costs time proportional to the total elements and also needs extra space for the merged array. The partition trick costs log of the smaller array's size in time and uses no extra array at all. In short, always reach for the partition trick when the problem cares about speed, and the merge only for a quick sanity check. If nums1 is empty, our infinity guards handle it since I just stays at 0 the whole time. Because we always binary search the shorter array, wildly different sizes never slow us down. Duplicate values are fine too, since the less than or equal check in our condition already allows ties. Remember that merge idea that seemed totally fine at first? It broke the moment the problem demanded log time. And that's exactly why we needed the partition trick instead. We binary search a cut in the smaller array, check 4 border values, and we're done in log time. New daily drops tomorrow, same time. I write these alone at a desk. A like tells me it landed. A follow means come back tomorrow. Ikmeyo. Advanced level, you already know the brute force merges OM plus N. Skip that pitch. The real question is whether you can find I and j such that the partition invariant holds without ever touching a merged array. That's the whole problem. Binary search on the answer, not on the data. This is the canonical binary search on the answer problem. The same skeleton shows up in K3 smallest in 2 sorted arrays, and in aggregation over sharded sorted data. The interesting part isn't the median formula. It's recognizing when a monotonic predicate lets you binary search a property instead of an index. Standard setup, you know it. 2 sorted arrays, combined median, O log min 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 required. The constraint that matters here is that it's log of the smaller size, not log of the total. That asymmetry is what forces you to always binary search the shorter array. Nothing new here for you. Sorted arrays, median, binary search. The only twist is that the binary search isn't over array indices in the usual sense, it's over the partition count, a virtual index that has to satisfy an invariant across 2 arrays simultaneously. You'd state this in one breath in an interview and move past it. Merge, index the middle, OM plus time and space. Worth mentioning only as a baseline you're about to beat, not as a real candidate solution. The gap between OM plus n and O log min mm is exponential, not incremental. No amount of micro-optimizing the merge gets you there. You need a fundamentally different structure, a monotonic predicate over a bounded search space. The invariant, pick I in nums1 and j in nums2, such that I plus j equals half the total length and max left I min right across both arrays. Because both arrays are sorted, moving I monotonically moves left once right 1, monotonically 2. That monotonically 2, that monotonicity is exactly what makes binary search valid here and is the property you'd want to call out explicitly if asked to justify correctness. Swapping to the shorter array isn't just an optimization, it's a correctness requirement. If you search the longer array, j could go negative for some I and you'd need extra bounds handling. Searching the shorter one guarantees j's meo blend plus n plus 1 once 2. I always lands in 0, NGO. The plus 1 in m plus n plus 1 sun 2 is what makes odd and even total lengths fall out of the same formula without a branch. For odd totals, the left half ends up one element larger, which is exactly the element the odd case return picks up. The sentinel infinities are what let iterate minities are what let iterate partitions without special casing array boundaries. Notice this never explicitly checks left 2 right 1 as a separate branch direction. If left 1 right 2 fails, left 2 right 1 is the only remaining failure mode, so the else covers it. That's the kind of detail that's worth narrating out loud. If an interviewer asks, why only 2 branches, not 3? Trace it yourself. But also think about what happens if nums2 were empty. Instead, does the sentinel infinity logic still hold with j pinned at 0 for every I? That edge case is the one worth having preloaded before an interviewer asks it. I1, J's1, left 1 1, left 2 2 2, right 1 inf, right 2 2 2. Invariant holds on the first probe. No need to warp the loop further. That's not luck, it's because low 0, highs 1 with 0 actually trace it. The search space here is small enough that the first or second guess usually lands, which is worth remembering when you're eyeballing a dry run under interview pressure. At this level, the brute force preamble is table stakes. The differentiator is what you say next. Go straight to, this is binary search on the answer. The predicate is max left, 5 min right, and it's monotonic because both arrays are sorted. So I'll binary search the partition index in the smaller array. State the invariant before you write code, not after. Worth having ready. The follow-up. Can you do better than O log minim? And you can't, not for arbitrary sorted arrays, since you need at least that many comparisons to locate the partition boundary in the worst case. Also worth mentioning proactively, this generalizes directly to kth's smallest element across 2 sorted arrays, same invariant, different target size for the left half. The ones actually worth stress testing out loud. One array fully empty I stays 0, sentinels do all the work. One array size 1 against a huge array. Thus the j never goes negative. And heavy duplicates across both arrays sitting right at the cut test that ache right at the ET is correct. Strict inequality would wrongly reject valid ties. The transferable idea isn't the specific problem, it's binary search over a monotonic predicate on a virtual search space rather than over concrete indices. That pattern recurs in kth element, across k list, capacity to ship in days, and split array largest, sum. New daily drops tomorrow, same time. I write these alone at a desk. A like tells me it landed. A line tells me it landed. A follow means come back tomorrow. Quick quiz. Our binary search runs in log of the smaller array size, not the combined size. Why do we search the smaller one? Pause and take a guess. Think about it for a second. We only binary search the smaller array, since the partition point in the larger one is calculated from it. Searching the bigger array would just waste steps. Round 2. What actually guarantees our chosen partition is correct, and not just some random split? Pause and think it through. Remember what we compare on each side of the cut. We compare the max of the left half against the min of the right half on both arrays. If either fails, we shift the partition until it holds, guaranteeing a correct split.